Good morning. It's Thursday morning, and we have one person in class, so I'm going to make the announcement over the screencast-o-matic, so it'll be on YouTube. So this is a company, I'm pretty sure. The name of it is STEM Jobs, and of course you know what STEM stands for, right? Science, technology, engineering, and mathematics, exactly. So you fall right in that, and all of you do. And this is STEM Jobs releases a new tool to connect classrooms to careers. The STEM Type Navigator allows students to match their interests to opportunities after high school. Well, you're well after high school. And this is from Pittsburgh in an effort to blah, blah, blah. So it basically lets students know about jobs that they may not have been aware were out there. The mission is to create career awareness and show students where there are real and relevant STEM careers that match their passions and interests. And again, this is a private business, I think, and so I'm pretty sure that I'm not sure why we're promoting it, but it came from our financial services office, which is and probably career planning as well. It's a company that matches STEM majors with job opportunities. So if you want to see more information about it, you're certainly welcome to come look. Okay. And Patricia is here. All right. That done, let's get started. We are still in Chapter 2, First Order Differential Equations. 2.5 is Solutions by Substitution. And there's three different types we will look at. And the first of these is homogeneous equations. Then we'll go to Bernoulli's equation, and then what they call reduction to separation of variables. Okay? So, any questions on anything we've done so far? All right, let me just say this too. I'm trying to remember to say this every class. This, of course, one of my best classes ever, okay? And yet, how many papers have come in from this class? 0, okay? Please, folks, don't forget about the research paper. It is a required grade. You know, it's not droppable, so please think about that. You've got did tell you about the good news, bad news situation next week, right?
We're off today.
That's the good news. Is Wednesday is a holiday, 4th of July, and that's the bad news. The bad news, you miss school that day. But the good neuse is it doesn't affect this class any because we're Tuesday, Thursday, so that's good news there. All right. But anyway, take advantage of your day off or the weekend or sometime and be working on the papers because that is a grade that cannot be dropped. Okay. Any questions then before we get going? And also, let's see, all but one person has turned in the first test, so I appreciate that. As soon as I get that last one in, then I'll return those to you. Okay. Because we are getting fairly close to the end of the chapter. All right, any questions? What we covered so far. Remind me what a homogeneous equation is. Now, we're going to run into the same name for different meanings later. What is it in this context?
Basically equals 0.
The what?
Basically equals 0.
That's the other meaning of homogeneous equations. In this context, a homogeneous equation is one in which the degree of every term, now it has to be a polynomial type equation, okay? And basically the degree of each term in the equation is the same. That's what, in this context, a homogeneous equation is, okay? And where we got to last time was the bottom of page 72, and here is the either one of these two substitutions you can use with a homogeneous equation to reduce the homogeneous equation to a separable first-order differential equation. Okay? And here are the two you may try. Let me get my pen activated. All right. Y say y and write u. Okay, y is equal to ux, or x is equal to vy. Okay, either one of those may work. Okay, you use the one that seems to fit the best. Okay, and it says to show this, observe that as a consequence of, okay, they went through a lot of action up here, okay, where the u is equal to y over x, so that would be y is equal to ux. When they plug that in, here is your original equation. Very generic form. M of xy dx plus n of xy dy is equal to 0. Okay? Now, that looks like our good old standard form for a exact differential. But now, again, what if m and n are not the right coefficients for that? In other words, when you do the test for exact coefficients, for exact equation, it fails. Okay? And the other technique we had, the integrating factor, it didn't seem like it was very promising either. Okay? So what do we do? Okay, but this must be homogeneous. M of xy, n of xy must have the same degree. Now, what do I mean by that? Okay? And again, they're polynomial-like forms. Make up an m of xy. Just make one up. An expression with x's and y's in it. To powers, additions, subtractions, whatever. Make up one. Any m of xy. Include both variables. Make up something. Any power, any variable, just make up something for m of xy. 2, 3, 7, 1, whatever terms. X to the fourth, you want a y in there?
X to the fourth, y squared.
Okay, multiplied? Okay, that'll be fine. X to the fourth, y squared. What's the degree of that? 6. Okay, that means the n of x, y. Whatever it is, every term in n of xy must also be degree 6. That's what we mean by homogeneous in this context. Later, what you said was going to be true. So in this context, that would make it homogeneous. So therefore, it's, and there's a possibility that could have been a exact, but no guarantee that it would have been. So we'll assume it's not. Okay. Now, what we're going to do is multiply both equations, okay? Well, I'm sorry, not multiply. If you see what they did back on equation 2, I don't know if we carried that out. It seems like we were running out of time and didn't quite get there. But if you rewrite your m of xy, and this is a legal move, okay, to equal x to the alpha m of 1u. Okay. Using this substitution, okay? Right? Okay. Okay. Now, here's, okay, in Curry's example before, he gave me degree 6 right here, right? So what we've done here is come up with a y equal to u times x. u times x, okay? Now, remember his x, okay. Yeah, that's right. His y was y squared, if I'm remembering right? So when you make it a u times x, the x is going to be squared, okay? To get it to the same degree, okay? If y is equal to ux, then y squared would be u squared x squared, right? Well, you already had a x to the fourth, so in this case, your alpha is going to be your 6. Because you have x to the second for the y squared, because we had x to the fourth y squared, if I'm remembering right. And if y is equal to ux, that would be u squared x squared. You multiply that by x to the fourth, you get u squared x to the 6. So x to the 6 comes out, and now you just have a function m of 1 and u, okay? Because you factored out the x's, and they were the x to the 6, and now you have your u in there, okay? Now, similar to that, your n of x, okay? Your n of xy, now we didn't make one, but we said it had to be the same degree. So if it's the same degree, meaning the sum of the x's and y's, the degrees of x's and y, has to be the same for every term, and you make that same substitution, then again, you're going to come up with x to the 6. They're calling x to the alpha here. So you can rewrite this as x to the alpha yuck. I get the writing faster than I'm talking, and I talk pretty slow, so, okay. N of 1 u, okay? That was your second substitute. I mean, that's where u is equal to y over x, okay? Now, rewrite this, okay? So we're using this substitution here and noting this. Oh wait, they do one more thing. Okay, so let's write that in there. X to the alpha m of 1u, and we're going to keep the dx in there for right now, okay, plus x to the alpha n of 1u dy is equal to 0, okay? Because this is equal to that, this is equal to that. We just plugged them in. Now what you might notice, okay, now be careful with this, but it's true. If you, we need something, here's the deal now. This had dx's and dy's in it. We basically lost our y's, okay? So let's take that expression there, your y, and do a differential of it, okay? What would that be? dy would be equal to what? Product rule. This expression here. dy is equal to? Say again? Okay, I think right here.
So use a variable in that?
Yeah, u and x's are variables, right.
Ux prime plus
u dx plus x du. Perfect. Okay? Now we're going to take that and put it into the equation we just wrote. Well, we're going to do one thing first. It doesn't quite seem fair, and this is why I said, this requires the x can't be 0. Okay? This is a requirement. But if when you look up here, this requires the x can't be 0. Because if x is 0, that means y is 0, okay? So a priori, x can't be 0, so since it's not 0, guess what we can do? Divide out x to the alpha from all terms, okay? And you lose them, okay? Now that doesn't mean you're rid of x's. X's is embedded in u, right? It's tied in there with it, okay? But that's not. So let me rewrite what we have now. M of 1u dx plus n of 1u dy is equal to 0. That's what we got from doing the last step. Now we're going, instead of the dy, plug in this, okay? And that would be m of 1u dx plus n of 1u. Instead of dy, we put u dx plus x du, okay? And that's equal to 0. Just substituted that dy for that one, okay? Now let's get our dx's together. This will be m of 1u, all right, sorry. This is 1, this is multiplied only by the n. May have looked like it was a binomial, it's not, okay? Only by the n, okay? So m of 1u dx plus un of 1u dx plus xn of 1u du is equal to 0, okay? All I did was multiply this and this across here, group these two together, and leave that one by itself, okay? Now, I kind of like to take it to the other side. The book left it together. It's kind of up to you how you want to do it, but note this. You have an m of 1u plus, I keep wanting to write mu because that's what we've been using, but it's not a mu, it's a u, okay? So if I sneak one in and miss it, take it out, okay? U n of 1 u, this is all multiplied by dx, okay, plus x, okay. Here's where I put the equal sign. Probably will come back to bite me here, but I like it this way, okay? I hit the wrong button. Okay, good. Is equal to, and you're going to have to negate it, that's the only downside to it, minus x n of 1 u du. Okay, because that was equal to 0, okay? Now, notice here, this is all a function of u. That's an x. Here's the only function of x, and this is all a function of u. So therefore, divide here and divide here. And that will produce this. Dx over x, which I think we know how to integrate, right, is equal to a minus x n of 1, I'm sorry, no, I've divided out the u, sorry. Not paying attention. Okay. We divided out the x, so we have n of 1 u divided by m of 1 u plus u times the n of 1 u du. Okay? There is our separated equation. Now they wrote them together equals 0. Don't know why, but I just prefer them this way. Now, I can integrate this. That's going to be log x. Now, again, I left off the parentheses, didn't I? Okay. Don't try to memorize this. That's a function we already took care of up here. That's a function, there's a u. Do whatever it takes to put those together. And if that's integrable, then you got it. Okay? It's taken care of. If it's not, then use that one and try it on y's. Okay? Neither of those work. Use numerical integration or something. We probably don't have a solution. Especially if you've already checked the exact and that doesn't work, and the substitution, the integrating factor with exact, and you can't get that to work, try this, and if this works, fine. If it doesn't, use numerical integration or something else. We just can't handle it, okay? But this is the next thing to try, okay? So let's do example 1, and I think you'll see all this abstract stuff makes maybe a little more sense, okay? So here's what we've got. X squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay. Now, sometimes my chair catches my cord on the computer and yanks it to the floor. I don't want that to happen, so I every now and then get messing back there. Okay. This looks like it is in the form for exact. What's your test for exact? This is a review. Okay, now you're jumping into homogeneous. That is homogeneous. Second power, 1 and 1 is second power. Okay, so it is homogeneous. I was just, for funsies, let's see what the test, review, what's the test for exact? Partial of this with respect to? To y. And what would that be? I think you said it, to y. Okay? And you compare that to partial of that with respect to x. Minus y, yeah. 2x minus y. Not the same. So obviously this is not exact. So don't try that. Now, let's not get into the integrating factor at this point. It might work. Let's see if this one works. Since it is homogeneous, it might work. Okay? Now, you have 1 or 2 substitutions to do. Do y'all remember what those were? The first was either y is equal to ux or x is equal to vy. One of those two. Now, I can't look at this and tell you which one's going to do better. Maybe with more practice and doing tons of these, oh yeah, that one's right. I don't use this that much, okay? So I don't think it's really going to matter. Which one do you want to use? Okay. Which one of those two? Those are your choices. That's your substitution. Which one? U of x. U times x, okay? Let's do that, okay? And again, don't worry about the formulas anymore. Let's just do what we've got here. So y is equal to u times x. So this will be, you tell me what the first term is. X squared. That doesn't change at all. Plus u squared, x squared. Is that what you said? Okay. I think you said ux squared in parentheses. I just separated them. And that's times dx, right? Plus, continue, x squared minus, okay, ux squared. Perfect. All right, we got one other little thing I forgot to do. Let's do this. What is your dy? You did it before. What's that? U dx plus x du. Okay, so instead of dy, we'll put u dx plus x du, and that's equal to 0. All right? Now, before I mess with that second term, and maybe I should have not done anything with that factor there, not messing with that, notice what we've got in every term. An x squared, right? So let's divide them out. Oh, is that even fair? Well, that goes, that goes, that goes, and that goes. Because when you divide that into 0, it becomes 0. Understood, x can't be 0, because you can't divide by 0, but obviously x can't be 0 in that substitution you did. Otherwise, that make y 0, and that would not be a very interesting problem. 0 plus 0 equals 0, okay? Not very interesting, so that's not going to happen. So x can't be 0. That's the only thing to keep in mind. So let's see what we have now. We have 1 plus u squared dx plus 1 minus u times u dx plus x du equals 0. Okay? Now, let's multiply these two, okay? Leave this alone for now. 1 plus u squared dx plus, okay? Now this is a sort of a binomial form, so let's go on and do it. Let's do the first. That would be a plus u dx. Now I'm not going to do it the way we usually FOIL. I want to do this one. Minus u squared dx, right? Now let's do the other two. Plus x du minus ux du. Did I do it right? And that's equal to 0. Okay? Now, let's get all the u's on one side, or du's, dx is on one side, and the du's on the other side. So this is going to be a 1 plus u squared plus u, right, minus u squared, whoa, look at that, dx. What do you notice there? You lose little u squares, don't you? Okay, that feels pretty good. And let's move to the other side. So I'm going to be moving the du's over there. So this is going to be a ux, because I'm adding it to both sides, du minus an x du, right? Agreed? Okay, I'm taking care of everything then. Okay, I reverse the order and stuff. Well, this one has a factor of x in it, so let's rewrite this as x times u minus 1 du. You okay with that? All right. Now let's just look at these two. Okay? Well, this is a factor of u alone. This is a dx. There's a factor of x alone, and these are all u's. Right? What does that seem like we can do? Separate the variables. So let's divide both sides by x and divide both sides by this thing, 1 minus u. And this will be 1 minus u. Okay? And those are gone. These are gone. And this leaves us dx over x is equal to, what is 1 minus u over u minus 1? Or u minus 1 over 1 minus u? What is this expression right here? Anyone recall? Okay, let me do something for you. Lessen that denominator, factor out a minus 1. Okay, one's a negative of the other one. You're absolutely right. So this will be minus u minus 1. And what's u minus 1 over u minus 1? Let's say 1, right? But it's got a minus sign. So this is going to be minus minus du. Now wait a minute. Can it be that simple? Yes, it can. And it is. What's the integral of the left? ln of x, I will put it in absolute values, is equal to minus u. And then I guess maybe a plus c. Okay? I don't know if I want to leave it at c or not. We'll come back and change it if we need to. But now we've not got to write what u is. Okay? U is y over x. Okay? And this is where we get the y's back into the problem. ln x is equal to minus y over x plus c. Okay? And frankly, that's as... let's see, do you want to solve for y? I mean, we could. So we could do this as subtract c from both sides, and you'd have, let's move the y over here, so that would be y is equal to minus x log x. We'll put in absolute value. And then it doesn't matter whether you put plus or minus, because c is a constant, plus cx. Okay, we multiplied everything but c. So that may be how they leave the form. No, it's not quite. Okay. Well, they do all sorts of mess to it. Goodness gracious, what did they do to it? I must have forgotten a term in here somewhere. I guess I did. Wait, I think I messed something up. Let me find what I did. Okay. How could I? It seemed like a pretty simple, straightforward thing. Okay, my second line up here is just what the book has. X squared plus u squared x squared dx plus x squared minus u x squared times that thing, exactly like I've got there, is equal to 0. That'd be a... yeah. Say again? That's what I was seeing. It looked like I got a sign wrong. Okay, and that's when I looked down here, I said, how did that happen? Okay, and that is exactly it. Okay, so that was way too easy. Okay, all right, so it's just from that point on. I could have left that there, but let's go back. Okay, I thought that seemed suspiciously too easy. And yeah, that should have been a plus there. and that would have been a plus there. So let's get rid of that too. All right. Up to there, I'm fine. Okay. Now, I think I see what happened. When I had done this through here, I interpreted that to be a minus, and that was really a plus. So sorry about that. All right, so here's what we got. dx over x is equal to u minus 1 over u plus 1 du. Okay. Now that is, yeah, that's what I need. Monica, right? Okay. I'll ask you, how do we proceed with this? In fact, I'm going to erase this and bring it over here because we're going to need more room. So while y'all are thinking about it, I'm going to erase it, okay? In fact, I'll write it first. dx over x is equal to u minus 1 over u plus 1 du. Okay? Now that I've got that rewritten, I'm going to erase it here. Because we're going to need all the room, well, maybe not all, but a lot of room. Okay? I'm still okay with this one. I think I can do that. Okay? This one, though, that's what I'm worried with. How in the world are we going to integrate that? I'm going to put the integral signs in, integrate both sides. But my question is, how do we integrate that? It's a pretty simple technique. You may not think about it. How would you say it? I thought about that. I'm not sure it's going to. I think there is a way to use it, but there's a little bit simpler way. Again? Okay. Integration by parts, you'd have to divide first, which may not be a bad idea either, because this is basically going to do the same thing. But here's something I think a little simpler than either of those. Try this one. And it may not work well, but let's try it. Let's break that into u du over u plus 1 minus the integral of du over u plus 1. Isn't that legal? You just put the numerator into two different integrals. This one and that. Is that all right? Okay. Now, this one, again, gets to be pretty easy. This one, though, that might be back to the same problem we had before. Okay? Except, maybe by parts would have been a bad idea, or possibly substitution. But I think what we need to do on this one, and maybe we should have done it in the very beginning, is the first thing you do when you try partial fractions, I think you said by partial fractions, is divide this into that. So let's go back and do that. I think that would be the better way. I thought there might be an easy way this way, but I'm thinking maybe not now. So what I'm going to do is take a little pause here, okay? Nope. Yeah. Okay. And let's do a division first. U plus 1 into U minus 1. Long division. How do you do that? You will go into U one time, right? 1 times U is U. 1 times 1 is plus 1. Subtract, which I usually change signs and add, and that will make it minus 2. Okay? That's going to be a 1 minus 2 over U plus 1. Right? Whatever your remainder is, put it over your divisor. Okay. So now that's a little bit better. That's going to be the integral of du, that's the one part, minus the integral of 2 over u plus 1 du. Yeah, we can do these. Can't we? We'll just take that one out. What's the first one over here? ln x. I'll put it in absolute value bars. Is equal to, what's that one? Integral of du? Just u, okay. Minus, and the last one I think you're already doing, 2 ln of absolute value u plus 1. And then we got a plus c. And this is where, now that I've looked at the book, I was suspicious they might do this, and I'm going to do it too because I think it's going to work better. Let's make it log c. It's a constant, okay? We're just going to make it log c. Of course, c can't be negative or 0, but that's okay. It's just a constant. Log c could be negative or 0, okay? But c can't. Okay. So I don't have to put it in absolute value bars because c has got to be greater than 0 for you to do it. Okay. Now let's see. I think now is the time to go back and plug in what u is. Okay? So it would be log absolute value x is equal to y over x, that's your u up here, okay, minus 2 times the log of absolute value y over x plus 1 plus log c. Okay? Now, I want to monkey with that middle one just a little bit. Let's make that x over x here. So it'll be y plus x over x. Is that okay? Now, I'm running out of room, so I'm going to go up to the top. And since we've already used our substitution, I think I can get away with erasing this. Okay? I'm going to leave that because we've used it, but just to remind you. Okay. So what we have now is log absolute value x is equal to y over x minus 2 times the log of y plus x over x plus log c. Okay. That's just a constant. Don't worry about it for now. Okay, I want to rewrite this slightly. Log absolute value x is equal to y over x. I'm going to have to erase some stuff, I think. Now, here's the part that hopefully you won't think is magic. Minus 2 times log absolute value y plus x plus, because, did anyone remember the rule for log of a quotient? Log of a quotient. Log of the numerator minus log of the denominator. Right? That's what logs do for you. They take one set of operations and drop them down to the next lower level. They can't do anything with addition and subtraction circles. They can't do anything with that. But with multiplication and division, if you had things multiplied together, that's the sum of the logs. If you had things divided, that's the difference of the logs. If you have a thing raised to a power, that's the 2 times the thing. So you change the power to a multiplication. Okay? So this becomes that. Now, I'm beginning to regret doing it. I thought I was going to make things easier. I think I will, but we'll go on with it. So what I'm doing here is minus 2 log of the numerator, and then it's going to be plus 2 log of the denominator. Okay? Because this minus that. We had a minus in first, so it's minus plus. Is that okay? You see what I'm doing? Okay. So that's going to be plus 2 log x plus log c. Okay. Now I've got to erase some more, sorry. So let's erase this. and that, and this. That was my long division. I sure hope I didn't make a stupid mistake there. Okay. All right. Now, notice you have a couple of log x's here. You can subtract this one from this side, and that'll wipe it out over there. So that leaves this side to be 0. 0 is equal to y over x minus 2 log y plus x plus log x plus log c. Okay? I don't think we can separate the logs here, can we? So what we're going to do is, yeah, I was right, you can't. So let me erase some more here. Now what I'm going to do here, I hope you don't find this too distracting. I'm going to isolate the y over x. That's what they do in the book, because all the other terms have logs in them. But of course that's going to move them to the other side. So that's going to be y over x is equal to, that makes this positive, 2 log y plus x minus log x minus log c. Now, that final one can be plus or minus, because that's just a constant. Who cares? Okay? But now we can combine their logs. Okay? So this is going to be, if we'll start this way, I'm going to have to erase some more. The calculus is, the differential equations are done. You've done that part. All you're doing now is getting it into a nice form. Okay? This answer basically is correct. Okay? But we're just trying to get it in a nicer form. Okay, this is the same as log of y plus x squared. Remember, we could do that to a logarithm too, right? Another rule of logarithm. Buy that? Okay. Minus log x. Well, let's move that into the denominator and make it absolute value x there. And by the way, we don't need the absolute value in the numerator anymore because that's squared. So let's just get rid of that one and just keep the absolute value of x in the denominator. Okay? We'll make this a parentheses, absolute value of x there. And then that log c, let's add a constant and put in front of it. So you have y over x is equal to c times the log of y plus x squared over absolute value x. Okay? Now that's one way to write it, or you can multiply everything through by x. Y is equal to cx times the log of absolute value, not absolute value, x plus y plus x, it doesn't matter, plus x squared over absolute value x. Okay, that's about as simple as I think we can write it, and let's see if that's what they get. Well, they don't, but they... Okay. Oh, my word. The C is messing us up here. Actually, what they're suggesting is I'll leave the C inside, which is what I meant to do anyway. The C is actually in here, not out there, the way we had written it. So let me move the C here and C there. Okay? Now, let me erase so I can clean that up. Let's start over here. Sorry, these take too much room and I have such a small screen. Okay. All right, let's see what we got. They left it as y over x, so let's do that. Let's go back to this form here. Y over x is equal to, And now they're going to combine all these things together. That would be a C x plus y. I'm going to change to x plus y squared. I'm sorry. Left off my log. C x plus y squared divided by absolute value x. Okay? Now, they do one other thing. They move the C downstairs with the x. Okay? We can do that. Okay? Or remember, C can't be negative. We just knew that at the beginning. So it can be anywhere down here. Okay? Now, what they do is take an e of both sides. And that gives them e to the log, e to the y over x is equal to, okay, taking the e of that be x plus y squared over cx. Now we can drop the absolute value bars because we're dealing with exponentials. Okay? Now, what they do now is multiply, finally, to get in the form they wanted, which any of these forms are fine. You don't have to get it in this final form, but I was just showing you all these answers are equivalent. Multiply by cx, and you have, I don't know why they chose this form, x plus y squared is equal to cx e to the y over x. Okay, that's what they wound up with. Why that's any better than one of the others, I'm not sure. Okay, but the hard part there was getting it into this form. The easy part was doing that. The trick you had to use here was do a long division. Okay, and that gave you exactly what you need. Okay. Of course, you have to go back and plug in what u is, and that was y over x. And everywhere you had that. And took a little bit of mathematical manipulation there. But it worked. Okay? Once you got that in there, any of those answers up above or here are perfectly good answers. Okay? Just whether you want it. Y is equal to x plus y squared is equal to, nothing special about one form over the other. In fact, I think this form right here is probably as good as it. Okay? But why they kept manipulating, I'm not sure. But they did. Okay. That was homogeneous equations. And generally, I'm not going to say they all work out this easily. The differential equation part was easy. It's getting it into the form they wanted. That was a little more work. But the other part, we got to that bottom part and then substituted in without too much grief. Okay? Well, here's another kind. Any questions on homogeneous before we leave it? Okay. So, let's go to Bernoulli's equation. Here's another kind of a differential equation. dy dx plus some p of x, this is looking familiar, isn't it? Times y, this is really looking familiar, is equal to some f of x, whoops, times y to the nth. Oh man, up until that y to the n, what was that form? Linear form. And we knew how to do that, okay? But then they stuck in a y to the n there, which definitely makes it nonlinear, okay? Definitely makes it nonlinear, okay? So you can't use a linear form, okay? Where n is any real number, that's called Bernoulli's equation. Now, what they don't say here, this book is sort of poor at that. They don't say which Bernoulli it was. Now, the reason I'll say that, there were two brothers, Johann, it seems like Jacques was the other one, but I may be wrong on that. They were both brilliant mathematicians, okay? And they sort of seemed to get along okay, but I bet you they had sibling rivalry like crazy, but I don't know that for a fact. And at least Johann, and maybe the other one too, had some kids. And generally, some of the boys were brilliant mathematicians as well. Daniel being one of them. Daniel Bernoulli comes up with a physics principle called Bernoulli's principle. It's what makes airplanes fly. Okay, he's just a brilliant, kid. I'm not sure it was him, but one of the boys, I believe it was Johann's boy. Johann was generally considered to be the top mathematician in Europe, hands down. I mean, he knew it. Okay, there was this prize that was being offered. Okay, sure. I could win me another prize. So he entered, knowing he was probably going to win. He was the top mathematician in Europe. What he didn't know is his son entered the same competition. And what really got his goat, his son beat him. Okay, he came in second. So what did he do? Congratulate his son? No, he kicked him out of the house. Okay, he said, "You're out of here, kid." So yeah, they were a rather dysfunctional family, it seems like. I say all that because that would be a pretty interesting paper topic, wouldn't it? Okay, but you decide. There's lots of things you can do. But anyway, I don't know which Bernoulli came up with this, but this is called Bernoulli's equation. Okay? Now, if n is equal to 0, what do we have? Yeah, you got the linear form. Okay? We know how to do that. Okay? If n is equal to 1, okay, this is also a linear form, right? Because then you can just divide out your y's. Okay? So that's pretty easy. In fact, that's separable, I bet. Okay? So, as long as n's not equal to 0 or 1, here's what we can do. Do a substitution. This whole section is solutions by substitutions. We saw what to substitute in a homogeneous equation. Y is equal to ux, or x is equal to vy. One of those two, substitute, see what you can do. Okay? In the Bernoulli's equation, now remember, n's not 0, n's not 1. Here's your substitution. U is equal to y to the 1 minus n. Okay? There's your substitution. Now, why can't n be 0? Well, we've already seen. No reason to do that. That would just be u is equal to y. If n were 0, there's nothing really to plug in there. Because, okay. And if n were 1, you just be u is equal to 1. And that would be a silly thing to put to. So, as long as it's not 0 or 1. Okay. So let's see what happens. If that's the case, what is du then? What would that be? See, I don't even think they do it that way, do they? No. So, let's not even mess with it. Okay? That just gets too confusing. Make that substitution. That's all you do. Okay? Now, I think the easiest thing to do is just to do the example and let that show, rather than getting all the potential hypotheticals in there. Let's just do it. So here's the problem. Can I erase this? Because I think I might need the room. Okay? Remember, that's our substitution. All right, so here's our equation. X dy dx plus y is equal to x squared y squared. Okay? Now, time out. That doesn't look like the same form we had, did it? Maybe I should have left that up there. How did that form begin? Okay, yeah, let's divide everything by x. That will make it look like it. Divide by x, divide by x, and divide by x. That goes to 1. That stays what it is. That goes to 1 there. So now we have dy dx plus 1 over x. That's now our p of x, right? Times y is equal to, our f of x is just simply x. And then you got y squared. So what substitution do we do? U is equal to? Okay, y to the 1 minus n. What's your n in this case? 2. So this will be 1 over y. Okay. So, okay. Well, okay, we wrote that. Now, I thought we needed to do this, but they held off on it for a bit. And I think the reason is so we could do this. Now, what we want is a substitution for dy dx. This is not a very convenient way to do it, right? Let me rewrite this for you. U is equal to 1 over y, right? It's hard to get a dy that way. So what might we do? What's an equivalent form to that? It's not that hard. Isolate the y. What would that give you? Y is equal, I say y is equal to 1 over u. Absolutely. Now that, let's take dy dx off. Okay? Now I don't see any x's in there, but let's do it. Of this right here, dy dx is equal to, let's do it this way. D of 1 over u, right? dx, because that's what your y is. Okay? Which is d of 1 over u du times du dx. Okay? Now, what is derivative of 1 over u? Or let's rewrite that as dy dx is equal to d of u to the minus 1 du times d. Yes, okay. Just a second since I'm writing this. Okay, what you say? Dy dx is equal to, say again? Negative 1 u to the minus 2, right? Times du dx. Okay. Now, find where we are. Okay. So that's our dy dx. That's what we're going to put in here. Minus u to the minus 2 du dx plus, now your y was 1 over u, so that's 1 over ux, xu, I don't care which way you say it, right? Okay, they say 1 over x times u. Whoa! I must, wait. I think I didn't flip enough times. Let's go back again. This is the trouble with trying to save space. Okay? Y is 1 over u. Oh, I see. I'm sorry. They skipped a step. Okay. I'm going to go back to what I just said. That's 1 over ux, okay, is equal to, where is it? There it is, okay. X and over u squared. You buy that? Okay. Now this is the same as minus 1 over u, right? 1 over u squared. So I think I'm going to write it in that form to make it easier to see. 1 over u squared. Okay? Now, looks like the obvious thing to do, multiply everything by u squared. So you got minus, and do we multiply by minus u squared? Yeah, let's multiply by minus u squared. Make that du dx minus u over x, that's how that happened, is equal to x. Okay? Now, what kind of form is that? That's a linear form, absolutely. Where your p of x is minus 1 over x, and alpha of x, g of x, whatever you want to call that, is just x. So yes, we can do that, okay, by our linear form. Now, let's review what the linear form says to do. What's the first step we do for that? So since I'm going to be doing this, I'm going to take out everything over here. Is that okay? Well, maybe not quite everything, but most of it. Okay? I'm going to take out everything down here, because we probably will need that at the very end. So let's remember that. So we'll leave that in place. Okay. What's the first step? Okay. What is your p of x? Negative 1 over x, right? And then we integrate that, and your integral of that, dx, is equal to integral of this. And what's that? Minus ln of x. Or you could say ln of x to the minus 1. I think that's what we need to do. That's right, it is ln of x to the minus 1. Okay? Or 1 over x if you wanted to. What's the next thing we do? Raise it to the e, and that's why I wanted it that way. And e to the that is 1 over x. Okay, that's our multiplying factor, right? So let's multiply it here, or integrating factor they called it. So that would be 1 over x du dx minus 1 over x squared u equal 1. Wow. Okay? Now, supposedly, this is the derivative of a square using the product rule, right? And what would be that square? That would be d by dx of 1 over x times u, right? Now let's just make sure that's right. So by the product rule, that would be 1 over x times the u dx, that part's right. Plus, the derivative of this would be minus x to the minus 2, which is that, times u. Yes, that's right. So this now is a perfect, that's a derivative, and however you want to say this, multiply both sides by dx and integrate, okay? And that gives you, this is a perfect derivative here, so it's 1 over x u is equal to x. Now we can put our plus c in there, right? We can multiply by x if you want to. That would be okay. So that would be u is equal to x squared plus cx. You okay with that? But we need to figure out what u is, and that's why I left it up here. U is 1 over y. So this is 1 over y is equal to x squared plus cx, okay? Which means y is equal to 1 over x squared plus cx, right? Now, I'm not sure that's the form they wound up with. Let's see if it is. Why do I keep dropping minus signs? Ha! Right here. I forgot. Product rule has a plus in it. And we have a minus there. So I talked my way through it, but it wasn't quite the same. It's plus or minus this. Is that right? So then this would be a minus 1 over x. Let's make sure that's right. Let's see. I don't think that's right. Okay, did I forget that at the beginning? I think I had it there at the beginning. I hate this. Okay, du is equal to that, is equal to, oh, there's where I lost it. They said that's supposed to be a minus x. And it was. See, I changed this to, I multiplied by, yeah. Remember, I changed that and said, let's multiply by minus u squared. And that gave us that, that gave us that, that gave us that. There's where my problem was. Okay? So this will be a minus 1, minus here. I'm still not sure. What's that? I'm sorry. My hearing's so bad, I'm not making it out.
And make it negative x once you integrate that.
Yeah, that's what I think it is, and I think that simply gets down to that. Yeah, negative x squared. Yeah, and that's where we messed up. And otherwise, yeah, it just carries through everywhere like that. So yeah, it was pretty easy to fix. Stupid to have made it in the first place, but easy to fix. Okay, so you see Bernoulli's pretty simple substitution. As long as that n is not 0 and not 1. Now, let's back off a minute. Notice what they said n needed to be. Not integer n, any real number n. Square root of 3. You know, negative 15/3. It could be anything other than 0 and 1. And that would still work. Yeah, that's pretty surprising. Not just an integer n. Their example was just an integer, but not that one. All right, so let's go to the next one. Any questions on that? Sorry about the dropping the minus sign. Okay. Okay. So the next one is reduction to separation of variables, which we have done in another with the homogeneous. It wasn't always guaranteed to do that, but it did. But here is another really generic form. dy dx is equal to some f of ax plus by plus c, okay? That's what your dy dx is, okay? Now, that's depending on what the f is. That's not necessarily linear. It's not separable. It's a mess, right? But here's the beauty of it. And it's about as simple a substitution as you can imagine. Let's do this substitution. Let u, our favorite substitutor, right, is equal to ax plus by plus c. In other words, the innermost part of that function on the right. That's what we're going to do. So let's see what we've got then. Dy dx then, okay, let's see what this gives us. If we take d by dx of this, that'd be du dx equal a plus b dy dx with nothing. C is a constant, right? So dy dx, let's subtract a from both sides. Du dx minus a. Okay, I'm just going to do that without writing it there. That's just in the way. Okay. Is equal to b dy dx. Okay. And then divide everything by b. And that's what you have here. Dy dx is equal to that thing. Okay? Not that we need it, but that's what it turns out being. We're going to deal with this side and play with that. Now, they don't give us any help at all there, except say use a substitution. So that's what we're going to do. We're going to use that substitution and try to solve. So here's what we got. Dy dx, this is example 3, is equal to, and here's what we got. A minus 2x plus y squared minus 7. Okay? With an initial condition y of 0 equals 0. All right. Now, nothing I can think. This isn't in any form that's recognizable with anything else. It's a mess, right? So that's some function of x and y. Okay? And so let's just take everything on the right and let that be our u. Looks like a simple thing to try, isn't it? So let's do that. Okay? Let u equal minus 2x plus y squared minus 7. All right. Now, unlike what I was showing you before, we really don't care, well, we do care about dy dx, but let's just do du dx. We're not going to come back and solve for it. We're just going to do du dx. What do you get? Ooh, this is going to take a little effort, but not too much. What would that be? Start me off. Oh, this is calculus. This isn't differential equations. We aren't supposed to remember that, are we? Sure we are. Chain rule, right? What would that be? Second? 2 times negative 2x plus y to the first power times negative 2 plus y prime, right? dy dx. Okay? Now they write it. And let me go on and write it as dy dx, because that's what they have it here. I was just trying to write it shorter because I was running out of room. Dy dx. Okay? Now,
you're integrating with respect to u, so why does the y not, or
okay.
why is the y a variable?
Okay. One more time.
In that case, you're integrating with respect to u, why is the y a variable?
Y is a function of x and u is a function of x. But hold off just a minute and let me see. I think we used the wrong substitution. Okay, let's back off. Sorry. I use the whole thing. It's so much simpler if we don't. Okay, because that -7 isn't doing us any good at all, and it's not really going to be very important. Okay, sorry about that. What's the innermost part of this function here? Of this thing here? The thing with our x's and y's in it. Okay, wait just a second. All right. Yeah, I think you said it. Negative 2x plus y. That's our u. The innermost part of it. Just a function of x and y. 7 has nothing to do with it. The square really has nothing to do with it. It's negative 2x plus y. That's your u. Now let's do the du. And you may have the same question, du dx. Okay, here's the deal. Y is a function of x. X is not really a function of x, it's just x. But u is a function of x as well. Okay? So therefore, when we take it, we have to do what, remember it was called implicit differentiation. Okay, that's what we're doing. So what does this give us? Negative 2 plus dy dx. That's it. Okay, bringing the other stuff with it just made it too complicated. Okay, so this implies that dy dx is equal to du dx plus 2, right? Yay or nay? Okay, just added 2 to both sides. So now that's what we put here. Du dx plus 2 is equal to u, I don't need a parentheses. Remember, we made the substitution now, so don't carry around x's and y's anymore. Bu squared minus 7, right? Now what would you do? Second? Yeah, that would probably be okay. I was more tempted to move the 2, subtract 2 from both sides. It might not be any difference, so du dx is equal to u squared minus 9. Okay? Now what? Absolutely. Separate the variables. It gives you du over u squared minus 9 is equal to dx, right? All right, write it in differential form. You don't want to have a dx. No, that's what it seems like you're doing. Okay, I'll do the right-hand side. How do you do the left-hand side? Partial fractions, absolutely. So how do you first write this? Let's see, I'm going to need more room. Second? I still think. Okay, factor the denominator is u plus 3 times u minus 3. Perfect. Okay, so I'm going to come up here and do what you're saying. 1 over u plus 3 times u minus 3 is equal to a over, you said u plus 3, plus b over u minus 3. Got it? Okay. Now, I need to find what a and b is. Second? Okay, you certainly could do that. Here's a slightly easier way. Okay, it's sort of doing the same thing. Let's multiply everything by u plus 3 times u minus 3. That, u plus 3 times u minus 3. And this, u plus 3 times u minus 3. This is sort of doing the same thing you did. Notice what happens here. You only have one here, right? Over here, sound effect included, you have a times u minus 3 plus b times, and here those go out, u plus 3. Now that's sort of easy to deal with, okay? And here's the part that I find a little problematic, but it works, so I'll do it. Let's set u equal to 3. Okay, what happens to here? That goes to 0. And that gives you, and if u is equal to 3, this is 6. 6b is equal to 1. So b is equal to 1/6. There we have it. So that gives you b is equal to 1/6. And now let's do something that seems not too fair either, but we'll do it. What if u is equal to minus 3? That's 0. And this will be negative 1/6. A is negative 1/6. Okay? Okay? Now let's plug that back in to this, and we'll have the integral. I'm going to do the 1/6 first. I'm going to put the 1/6 out front. I'm going to do the b first, and b was over x, u minus 3. That would be, du over u minus 3 minus 1/6, the integral of du over u plus 3, and that's equal to x plus c. We may need to change the c in a minute, but we'll see. What does the first integral give us? 1/6, the log of u minus 3 minus 1/6, the log of u plus 3 is equal to x plus c. I want to say, I'm going to put log c for a minute here, okay? I may change my mind on that, but I'm going to leave it open, okay? Now, the question is whether to try to simplify this as is or not, okay? I'm going to pull out the 1/6 and make this as log of u minus 3 over u plus 3. I may be doing this way too soon. And let's just get that c over here. Just imagine that's a minus log c. When you add that to it, I think that just puts the c there. I'm not absolutely sure. I'll have to come back and check that. And that's equal to x. Okay. Well, that's not a 4, that's a c. Okay. At some point, we need to go back and put in what u is, or u are, or whatever. So I think what we have here is that, let me let me see how they did it, because okay, you've got exactly the same thing I have. Okay. Let me go back, and I'm going to change back to what I had before. I had the 1/6 there, and we had a plus C here. They called it C1, so I'll put it C1 so it'll look the same. That's exactly what they got. And frankly, that's well, it's not quite a great answer yet, okay? But what they're going to do, and this is, they're going to multiply both sides of the equation by C, okay? By 6. And that gives them log of absolute value u minus 3 over u plus 3 is equal to 6x, and here is where their sleight of hand comes. We'll leave the plus C1 for right now, okay? And then they're going to take the e of both sides, okay? So the e of log is just going to leave us u minus 3 over u. I can't write down here because I'm in the mess. So I need to go somewhere else, sorry. Let's go up here and erase this because we've already used this. We got what we needed. It's already been used, incorporated in the problem, so we don't need this anymore. I'm afraid we might need something else there. Maybe not. I don't think so. So let me erase this too. I'll just keep the substitution because I need that. I know I'll need that. Okay. So where this is going to go next is up here. Take the e of both sides, and that just gives us absolute value. Well, we can lose the absolute values here. Well, we'll keep them for now. U minus 3 over U plus 3, okay, is equal to e to the 6x plus C1, okay? But you see, an exponent of a sum is the product of the exponents. So e to the C1, you can just make that a constant, and that will be the same as c e to the 6x, okay? Now, and like I said before, I said it but I didn't do it, you can lose the absolute value bars because you're no longer dealing with logarithms. Seems to be cheating, but it's okay. And now what we're going to do is plug back in what u is, or u are, or whatever. So this would produce u is minus 2x plus y. I'm going to write it as y minus 2x. It writes me to start with leading with that. So let's just make it y minus 2x minus 3 over y minus 2x plus 3 is equal to c e to the 6x. Okay? Now, there's nothing wrong with that answer, okay, at all. Oh my, they did something different. Wait a minute. Let's go back and do it the way they did because it does come out simpler. But there's nothing wrong with this answer here. That's perfectly correct. But what they did is not plug in yet. They simplified here. And their simplification is not quite so simple. Okay? All right. Multiply by u plus 3. So you have u minus 3 is equal to u plus 3 times e to the, times c e to the 6x. C e to the 6x. Okay? Now, this is a lot of mathematical manipulation. It doesn't get you very much, but it does make a few things a little simpler. Okay, u minus 3 is equal to u c e to the 6x plus 3c e to the 6x. Okay? Now let's get all our u's together and things without u's apart. So that's going to add 3 to both sides and subtract this one from both sides. U c e to the 6x. Okay. I'm going to erase some more so we can write. Okay. I think we're through with this, so I'll get rid of that. Hopefully not have to use it again. And that's already done, so we'll get rid of that. And I think we can get rid of this and this. We've already used those. And I think we can get rid of those. That may give us enough room to work with. Oh, we probably don't need this either. I'll leave something down here. I don't think it's useful, but I'll leave it. Okay. This just takes way too much time to get it into the form they like. Okay, so what we have on this side, the 3's went out, and we have a u times 1 minus c e to the 6x is equal to, and over here, these went out, and you have 3 times 1 plus c e to the 6x. Okay? Then divide both sides by 1 minus c e to the 6x. 1 minus c e to the 6x. Okay? So these go away. Now plug back in what u is. And u is y minus 2x. So y minus 2x is equal to 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. And then add 2x to both sides. Okay. So your final answer is y is equal to 2x plus 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. Getting into an explicit solution of y sometimes takes an awful lot of work, but that's how you get there. Okay? And that is the answer that they got. Okay? Well, sort of. I put the 3 on the outside, they put it on up with the numerator. Okay. Now they do something completely, I forgot. I completely forgot. This was an initial value problem. Okay? So we could have figured out what the C is. So y is equal to 0 when x is equal to 0. So let's plug that in. Figure out what C is. Okay? Now, I wish I hadn't have taken so much room, okay, for my answer. I was thinking I was through. Okay. I hope I won't need this again. So when x equals 0, y is equal to 0. So let's see what this tells us. 0 is equal to 0 plus 3 times 1 plus c to the 0th power, which is e to the 0th power, which is 1, over 1 minus c times 1. Okay? So, divide both sides by 3. That's out of there. Still 0. So that's equal to 0. I'm sorry. That's equal to 0. Multiply both sides by 1 minus c. And that goes away. So you have 1 plus c is equal to 0. C is equal to negative 1. So go back in here, rewrite this as 2x plus 3 times 1 minus e to the 6x over 1 plus e to the 6x. There's your answer. Okay? 2x plus that. Yeah. Now they didn't put the exponentials in one fractional form. They did the 3 times, but it's the same thing. Now, I'm not about to draw the graph for you. If you got your book, you can see it. But this is the family of curves with different c's in it. The one where c is equal to negative 1 is the blue curve there. And that's where when x equals 0, y is equal to 0, so that's where it crosses the origin there. So of all those curves, that's the one we'll use. Now notice it's asymptotic behavior here. When x gets very, very large, this is approaching 2x with one offset plus 3, and the other is 2x minus 3. So this would be the asymptote here is a line with slope 2 and y-intercept minus 3, and up here is slope 2 with y-intercept plus 3. Okay, so that is your graph for you. I hope I never have to draw them, but anyway. All right, that's that. We finished 2.5 finally. Okay, homework exercises here. They tell you the first 14 actually, they say are homogeneous. So do any of the first of the odds 1 through 9, and 11 through 14 are initial value problems, so do either 11 or 13 or both. Then they tell you each differential equation in 15 to 22 are Bernoulli equations, so do any of the odds 15 through 19, and then 21 is an initial value problem, so do that one as well with an initial value problem. Then they said 23 through 30 are of the reduction to separation of variables. So do any of the odds 23 to 27, and then do 29. Those are general. 29's initial value, so do that. The discussion problems, you can look at if you'd want to. One reason to look is there is, on 35, is a Riccati's equation. Who in the world was Riccati? Okay? It's sort of based on the Bernoulli equation, but a little bit different. So you don't have to do his equation, but that might be a potential paper topic. Now, there's another one in here, number 38, is talking about a logistic equation. And I don't know what areas y'all are going into, but my wife is an epidemiologist, and she uses logistic. She's not doing population growth. She's looking at disease growth, which basically is the population of a virus, like the flu virus or something like that. So if you're going into any kind of medical research, like if you're a biomedical engineer or something like that, you're going to run into logistic equations. So you might want to take a look at that as a possibility. All right. Now, is it really almost 10:10? Yeah. I didn't know we were almost out of class. I was going to say let's take a break. But since we got just 2 minutes left, let's just basically get started in 2.6. Sorry about that. I want to give you a break. In fact, when Curry got up to go out, I said, well, I ought to stop and have a break now. But I thought, nah, let's finish this. Okay. I think I've been saying all along, to some extent, you know, these techniques are out there, and you can sure use them when they fit, but a lot of times they're not going to fit, okay? And there's just not much you can do. So basically, I've said it before, you go and solve it numerically. So we're going to look at, in 2.6, some really simple numerical approaches. They have much more sophisticated than this. In fact, later on in the book they do it. I just don't think we're going to have a chance to get there. So at least to get you introduced to it, this is what we're going to do next, is numerical method. And I don't think we'll really get going there. I don't know, I'll just cheat you out of 1 minute of your tuition dollar, okay? Will you live with that? All right. So y'all get to go early. A big 1 minute early. Good deal. Any questions? Okay, I'll try to, in fact, I already have your test ready for you. It's just you haven't done the numerical part, so do any of you want to go on and get started on the first part of it now? Okay. If you still haven't turned in the first test, I would say get busy on that one. But you see, the only person who hasn't turned that in is not here. So I think I have these. I know I had to run them off yesterday. Sent them down to be run off yesterday, but I just don't recall if I got them back. Yes, I did. Okay. Stiffen the joints. Okay. Like I said, it's just the last problem, Euler's problem, number 9. It's the only one we haven't covered in class. Okay? But more priority is get going on your papers and get going on your first. All right, you already printed the first test. That's right. Okay.
It has to be 2 pages.
I'm sorry.
2 pages. The paper.
Yeah, the paper, 1 to 2 pages. Okay. Yeah. Don't have it shorter than 1 page of text. I described what that was. If you run over 2 pages, there's no penalty for that. But if it's too short, there is a penalty.